In this video, we're going to take a look at measuring the special case of a power rail. That means the DC voltage supplying power to some. What makes it a little challenging is it's a large DC voltage, and we want to see a small change in that DC voltage. That means that we're going to have to zoom in on that DC voltage to see small changes. We'll use as examples the three different power rails on an Arduino. And one of the other important principles that we're going to illustrate is this idea of the ground reference level, whether it is floating or whether it is common. And we'll see the impact of that and the difference in this measurement. So we're going to look at how do we measure those small changes, and I'm going to show you a couple of tricks we can use in order to simplify this measurement. We'll zoom in, and then once we've zoomed in, we'll look for some periodic features on the power rail to trigger on, and sometimes there isn't any, and we'll just be looking at that noise level on the power rail. Let's start out with a really simple measurement. Now you'll notice that we have on the 82 scope, we have the female sockets, and on the Arduino we have female sockets, and in order to make a connection between the jumper wires and the Arduino, we need to add a little gender changer plug in there. We're going to start out measuring the 5-volt rail on the Arduino board when we use the USB to power it. And so let's just connect that up. We're going to have the channel 1 minus going to ground and the channel 1 plus going to the 5-volt. And so when we plug in the USB that'll power the Arduino board, what do you expect to see? We should see a 5-volt signal. Let's take a look at that. So we plug it in. It powers the Arduino, it also starts running whatever code happens to be running in there. Let's take a look at the noise on that 5-volt rail. We turn on the scope. Of course, it's going to come up in the stopped mode, so we have to trigger it, turn it on. We ought to see about a 5-volt signal. I'm going to turn off channel 2, we're not using that. Where's channel 1? Well, it should be about 5 volts. Look at the scale. Oh, here's 2.5 volts. We're off scale. You can just barely see the hint of something at the top here. This is where understanding what you expect to see, rule number 9, thinking about what you expect to see is really important, because that says clearly we're off scale. So let's change our scale. We'll make it 2 volts per division. Here we go. That's great. Here is 2 volts per division, and here's our 5-volt rail, just like we expected. One of the first questions we'd like to know is, well, what exactly is that voltage? It's about 5 volts. How close to 5 volts? And that's where we can use the measurement function to get us a little closer now that we know what to expect. So we come up here to measurements, and I'm going to add a measurement. This is a defined measurement. It's the average in channel 1. It's a vertical measurement, it's a voltage. I want to display the average of all the measurements in this buffer. So I add, and we're done. And you can see it's fluctuating. So it's taking all the measurements in this buffer, all 8,100 of those measurements, adding them up, taking the average, displaying that number each time it takes that measurement. And it's fluctuating around a little bit. That's why I like to see the average of that measurement. So it's the average of the average. So I'm going to show average, and we'll do a quick reset. And now we're taking all those buffers, doing all the measurements, the average of that voltage, and we're displaying the average of that over time. 4.94 volts, pretty darn close to 5 volts. In fact, if it was 50 millivolts out of 5 volts, that's 1%. So we're a little bit larger than 1% off, maybe 1.2% off from 5 volts. That's great. I'd really like to see the noise on top of this. If I were to expand the voltage base and zoom in on that, when I try to do that, here's 1 volt per division. It's pegged me off scale. I'd have to type in an offset over here and pull the 0 point down below, or I can grab the caret and move him down. And then if I change the voltage scale again, it's going to go off scale. And so here's the trick that I'm going to use. So let's go back to an offset of 0. So now we're where we were before, off scale. Let's go back and bring it on scale. So we'll go to 5 volts a division. When we expand the vertical scale, we're expanding about the center. If I move my signal into the center, then when I expand the scale, I will be expanding about that signal. So I'm just going to grab that little caret that defines the ground. I'm going to offset it so that my signal is in the middle. And now when I expand the scale, here's the trick. Here's 2 volts. Here's 1 volt. I'm always expanding about this range, I don't have to worry about the offset. And you notice we're at minus 5 volt offset. That means that if here's the center of the screen on this scale, the center would be at the 5 volt range. So here's a half a volt per division, 200 millivolts per division, and now we're beginning to see a little bit of the noise on top. We're still getting the average value, the 4.36 volts or so as the average, and we're able to see a little bit of noise starting to appear here at the 200 millivolts per division scale. Let's go to 50 millivolts per division, and now we see a little bit more of the noise. Let's take a look at the 3.3 volt line. So we're just going to move over to the 3.3 volt rail. And of course we have to change our offset here, and we can do that by literally just typing in minus 3.3 volts, and there we are, we're on scale. We can get a little bit closer. We'll drag the offset to the center here. Our average is taking that buffer, taking the average. Let's zoom way out so we can see a little bit of the low frequency noise. And wow, not a whole lot of noise. I have to reset my average. It's pretty darn stable, 3.24 volts. Again, we're within a little bit more than 1% of the DC value that we're rated at, 3.3 volts. Pretty darn good. Very little noise on that rail. So these two rails look great. Now we've looked at the power rails when we supply power with the USB hub. Now let's look at when we supply power with the 9 volt jack. So we're still going to be, when we plug the 9 volt in, we're still going to be using the onboard regulator, so that shouldn't change, even though we'll be powering it with the external power plug. So we plug the power plug in, and not much change. You get the same voltage, same low amount of noise. That's great. Let's take a look at the 5 volt rail. So we would set the offset at 0, change the voltage scale to something more appropriate, 5 volts per division. Hey, there it is. It's coming out at pretty darn close to 5 volts. We'd like to expand on that to see more detail, so we move this to the center, and we just expand the vertical scale. So here we're at 50 millivolts a division. Oh my gosh, look at that. This is 20 millivolts a division. So that's less than 0.5% per division. And look at the noise level, incredibly stable, because it's really defined by an onboard voltage regulator. And then lastly, let's look at the 9 volt coming in. So this is going to be the raw voltage coming in on this power supply. Let's see where that is. That's V in, and now we're looking at V in. Now that's 9 volts, so of course we're off scale. So here's what we're going to do. Always a good policy. Let's make the offset 0, and then let's zoom back out so we can see the whole thing. So here we are at 5 volts a division, and okay, here's roughly our 9 volts, and sure enough, well, it's 8.6 volts. Now that 9 volt is not a spec value, it's roughly 9 volts, so we're not too surprised it's not exactly 9 volts. Let's expand on this and see the noise on that. So we're going to move our center down. We've got it, the signal coming in, that DC voltage centered on the screen, and now we can expand on it. So here is a volt per division, pretty stable. So by changing the time scales and the voltage scale, we're able to zoom in and take a quick look roughly at what that DC noise level is. And we see in all cases it's significantly, the DC absolute value is within about 1.5% of what we expect it to be, its specified value, which is great. And the noise on top of that in this environment that we've been looking is about significantly less than 1%. So there's one last effect that we're going to take a look at. Right now we have the USB plugged in and the power. That power plug that we have coming into the Arduino has an outer shield and it has the center plug. The center plug to the outer shield is about 8.6 volts. The shield of the power plug is floating. There's no connection between the shield of that power plug and the outside world, because inside of the AC to DC converter is a transformer that isolates this ground, this outer shield conductor, to anything else. There's a voltage between the outer shield and the center voltage. That's the voltage difference, that's the power. When we plug that shield onto the board, that shield gets connected to the ground plane or the ground conductors on the board, and we distribute a 8.6 volt between the power rail and the ground conductors on the board. But the ground conductor on the Arduino board is connected through the ground of the USB hub, which ultimately goes back to my laptop, which also connects to the ground of the 82. And so the ground of the 82 is connected to the ground of the Arduino board, and so they're at the same voltage. But suppose I don't have the USB connector plugged in. When I have the 9-volt plugged in, and I measure this voltage, and let's zoom out on that voltage. When I measure the voltage between the input voltage on the plug and the ground on the board, that's the difference voltage between the 1 minus input and the 1 plus input. I'm measuring that voltage difference. It shouldn't matter whether I have the ground on the board connected to the Analog Discovery 2 ground, or if it just sits there floating. I'm just going to measure that absolute voltage difference, and that's independent of the relative voltage of the ground on the board. Absolutely correct, except that if the actual voltage, if I were to stick a voltmeter and measure the voltage between the ground conductor on the Arduino board and the ground conductor on the Analog Discovery 2, if that voltage is greater than about 7 volts, then the poor Analog Discovery 2 sees that voltage difference between the grounds and gets confused. The input gets saturated a little bit and we get additional noise. I have to have the ground voltage on the device that I'm measuring within 7 volts of the ground on the Analog Discovery 2. By connecting in the USB plug to the Arduino board, I've done that because this ground on the Arduino board connects to the shield of the USB cable. That goes back to the USB hub. That goes back to the laptop. That goes back to the connection to the Analog Discovery 2. And so those grounds are within 7 volts easily. And I get a great measurement of the difference voltage. But watch what happens when I unplug that ground connection. Now I have isolated the ground between the board, because that board ground is connected to the shield of the AC to DC converter, which floats. There's no connection between that ground and the outside world. And so there's a voltage shift, the noise, the AC power line noise voltage fluctuation between the ground conductor on the board and the ground conductor on the Analog Discovery 2. We call that difference, we call that voltage the common voltage difference between those two grounds. And if those voltages are different than about 7 volts, then the poor 82 is going to give us additional noise. This voltage noise that we're seeing on the screen, which looks like, if I switch it to 10 milliseconds of division, you can see it's got this periodicity to it. Let's use the trigger to trigger on the pattern. Here we're triggering on that pattern, and you can see it's got some periodicity to it. What's the period of that? Well, it's about, let's see, 10 milliseconds. Here's one cycle, here's another cycle. Let's see, so here is 10 milliseconds, about 16 milliseconds. Let's use the cursor just to give us a little bit better measure of that. So here's the 0, pretty much the 0 at the start, and then here's the beginning of the next cycle, and hey, about 16 milliseconds. What's the frequency if the period is 16 milliseconds? That's 60 hertz. That's no coincidence. We're seeing 60 hertz noise has nothing at all to do with the voltage difference between the V plus and the channel 1 plus and channel 1 minus, that differential voltage. Has nothing at all to do with that differential voltage. It has to do with the fact that the ground on the device I'm measuring that I'm looking at the voltage difference of, that ground on the device is way different from the ground on the 82. And it's that common voltage noise at 60 Hertz that's screwing up my measurement. It's an artifact of the measurement. And that's why it's really important to think about the device that I'm measuring. Where is his ground ultimately connected? If ultimately they're connected to the same ground as the Analog Discovery 2, then I won't have this artifact. But if the ground on the device I'm looking at is floating, then I'm going to have an artifact. I'm going to see that common voltage noise. And how do you fix that problem? That's why we have ground connections to the 82. As long as it is safe, as long as there's no safety there are no safety issues, then I'm going to connect the ground of the 82 to the floating ground of the board, and it won't be floating anymore. It'll be tied to the ground on the USB hub. So I have conveniently another ground pin over here. So watch what happens to the noise when I connect in the other ground pin. And look, all of that AC 60 Hertz noise has disappeared because now I don't have a voltage difference between the ground on the Arduino board and the ground of the 82. I get exactly the same effect if I were to come along. So here's our noise. I got a floating ground on the Arduino board, and now all I'm going to do is I'm going to touch the outer shield of the USB, which is the ground connection to the USB hub. I'm going to touch that the outer shield of the USB connector shell here, which is connected to the ground of the board, and watch what happens. I just touch them together, and now I'm connecting those grounds, and that common voltage difference has disappeared, and the artifact has disappeared as well. So be very careful when you're measuring power rails. Depending on the source of the power, if the ground of the power supply floats and the ground of the device we're measuring floats compared to the ground of the Analog Discovery 2, we will have this artificial noise problem because of the difference in the common voltage, and that's where we want to bring those grounds into the same common voltage, and that's where making a connection between the grounds of the device under test and that's where making a connection between the ground of the device under test and the ground of the Arduino with one of the ground wires is such an important thing to do to eliminate this common artifact.